Okay, we're group 3 and our project is on exponential growth and decay. And I'm Olivia.
I'm Jocelyn.
I'm Adriana.
And I'm Brittany. Okay, so the definition of exponential growth is the mathematical change that increases without a limit based on the exponential function. And the definition of exponential decay is the mathematical process of reducing an amount by a consistent percentage rate over a period of time. How exponential growth and decay are used. We use it with this equation, P of t equals P sub 0 e to the power of k times t. The variables represent P of t is population, P sub 0 is the initial power, k is the constant, and t is time elapsed, so seconds, minutes, hours, days, years. And e is Euler's number, which is equal to 2.71828.
So exponential growth and decay are important in analyzing trends in data and have real-world applications and relevance. They can be used to interpret change across data and predict future changes based off the function of data. So a few examples of how they're used in STEM careers. Coroners use exponential decay to predict the time of death and dating of the body. Radiocarbon dating is used by archaeologists to date back thousands of years on all types of organic materials based on the decay of carbon-14. Ecologists monitor population growth and change, which is similar to the problem that we're doing. And many business people and individuals involved in stock investment use growth and decay functions to make predictions in the market.
Concepts of exponential growth and decay. An important concept of exponential growth and decay is that the rate of change will continue to increase or decrease. Natural log is different from log because it uses Euler's number e as its base instead of log base of 10. Euler's number e is equal to 2.7183. Natural log follows the basic rule. E to the power of ln times x is equal to x when x is a real number. This rule is critical especially when trying to solve for k, the rate of change, or t, time elapsed, given they are exponents of e in the growth or decay function.
So for our first example, it says, find a bank account balance if the account starts with $100 and has an annual rate of 4% and the money is left in the account for 12 years. So to solve this, we start with what we know. We know the exponential growth equation is P of t is equal to P sub 0 e to the k times t power. E is equal to 2.71828. P of 0 is $100. K is equal to 0.4, which is 4%. And t is equal to 12, time in years. So we plug what we know into our equation. So we have P of t is equal to 100e to the 12 times 0.4 power. And then using a calculator, we plug in the equation to find what t is equal to, which t is equal to 161.60. So that means after 12 years, there will be $161.60 left in the account with a 4% rate.
So example 2 was our given project problem. So it states COVID-19 or any disease can spread like wildfire. Suppose COVID-19 grows exponentially and there was only 100 cases initially. After 12 days, there were 100,000 cases. Find the function to model COVID-19 cases after t days. So that has to be our first step. And then for B and C, we can use the function from step A to solve. So then we're going to look at how many cases there were after 15 days and how long it would take for 7 billion cases to occur. So first, to find our function, we're going to plug in our known variables into the parent exponential function. So the data given by the prompt is that P, our initial population was 100 cases, and then our P of 12, so after 12 days was 100,000 cases. So first we have to find our rate of change. So we have P of 12, 100,000 equals 100 E raised to K times 12. So to solve, you just divide by 100. So then we have 1,000 equals e raised to the k times 12. And then we're going to apply natural log to cancel out our e. So we're going to apply natural log to 1,000 and then to the e. And the k times 12 comes down from the exponent and becomes a whole number because e times log, natural log cancels out. And then we divide by 12 to isolate k. So we have the natural log of 1,000 divided by 12 equals k, which doesn't simplify to a predictable rate. So we just leave it as a fraction. So now we have our new function, which is going to be p of t equals 100 times e raised to 1,000 times natural log divided by 12 times t. So then for part B, to solve for how many cases there will be after 15 days, we just plug 15 into the exponent t for time to solve. So we have p of t equals 100 times e raised to 1,000 times natural log divided by 12 times 15. Once we plug that into a calculator, we get roughly 562,341 cases. And then for the last part, to find how many cases or how long it will take for 7 billion cases to occur, we just plug 7 billion into our end population and then solve for the variable t. So we have 7 billion equals 100 times e raised to 1,000 times the natural log divided by 12 times t. So again, to isolate the variable t, we have to keep in mind the relationship between natural log and e. So the natural log in the exponent will cancel out with the e, and then just solving for t will come down to roughly 31 days for the virus to spread to 7 billion people.
Example 3. This is an example you guys would work on. So let's go over it. A gray squirrel population was introduced in a certain county of Great Britain 30 years ago. Biologists observed that the population doubles every 6 years. And now the population is 100,000. So first step would be, what was the initial size of the squirrel population? The second one would be estimate the squirrel population years from now. And the third step would sketch a graph of the squirrel population. So we'll give you a couple minutes to work on this example. Example 3 explanation. For us to solve this problem, we would use our exponential formula, which is p of t is equal to p sub 0 e to the power of k times t. We know that the population would double every year, so our t would equal 6. Now the population after k equals 30 years is 100,000, so p of 30 is equal to 100,000. Now let's solve our equation. P of 0 to the power of 30 divided by 6 is equal to 100,000. P of 0 times 2 to the power of 5 is equal to 100,000. P of 0, 32 is equal to 100,000. Now we would divide both sides by 32 to get P of 0 by itself, which gives us P of 0 would equal to 3,125 squirrels. For B, now that we have found our initial population, P of 0, the squirrel population after t years is P of t equals 3,125 times 2 to the power of t divided by 6. For the number of squirrels 10 years from now, set t equal to 30 plus 10, which is equal to 40, in the equation above and estimate P of 40. So we would do the same steps that we did for A, which is P of t is equal to 3,125 times 2 to the power of t over 6. P of 40 is equal to 3,125 times 2 to the power of 40 divided by 6. We would simplify that exponent to 20 divided by 3. And so P of 40 would be equal to 317,480.210394. And we would just round that up to our nearest integer. So we would get P of 40 is equal to 317,480. And for C, we would just plot our points into a coordinate plane.
So here are our conclusions and possible issues. In conclusion, exponential growth and decay functions can be applied in many ways and can also be manipulated to solve for any of the variables in the function by using the relationship between ln and e. And one possible error would be using log with a base of 10 instead of natural log with base e.
Thank you.
Thank you.